Dear Chairman, dear participants, good afternoon. This report is presented on myself and my supervisor Valery Shlyannikov from the Laboratory of Mechanics of Deformation and Fracture. The topic of my report is multiphysics finite element analysis and measurements for thermo-mechanical fatigue regrowth rate testing applications. Outline of my talk is the following. First is introduction, then thermo-mechanical fatigue test equipment. Next chapter, multiphysical finite element analysis of strain-stress state under thermomechanical fatigue conditions. That includes calculation methodology, then electromagnetic analysis of the induction heating process of the specimen, and CFD analysis, strain-stress state analysis in the specimen. And finally, I will show results. So, a few words about the timelines of the problem. Thermomechanical fatigue is perhaps the most typical loading of the structural components operating at elevated temperatures, in particular in modern turbofan engines with a high compression ratio in an axial compressor. The air temperature at the compressor outlet is comparable to the temperature in the disk of the first stage of the turbine. At the same time, in the process of starting and shutdown, loading occurs non-isothermical. It stands to reason that it is important to take into account the thermal condition of the component during operation. We have carried out the following types of tests to investigate the effect of thermomechanical fatigue loading conditions on the structure of the material and on the characteristics of the crack growth rate, namely isothermal test under harmonic loading and with load hold at peak stress. The temperature range is chosen 400 to 650 degrees Celsius for in-phase and out-of-phase cycles. The cycle period is 60 seconds. I will list the equipment we use for thermomechanical fatigue tests. The slide shows the geometry of the specimen tested at thermomechanical conditions. The material of the specimen is chrome-nickel alloy XH73M. Thermomechanical fatigue tests were carried out on a Zwick-rule servohydraulic testing machine. A pyrometer directed at the specimen monitors the temperature at a point on the surface of the specimen working area. A rectangular induction coil with photons was used. During the test, the crack opening displacement was measured via extensometer. The test, carried out at thermomechanical fatigue conditions, require a numerical analysis for following processing and strain-stress state analysis in the volume of the specimen. For this purpose, an algorithm was developed for the multiphysical calculation of induction heating of the specimen, convective cooling and strain-stress state calculation, taking into account all the features of the temperature cycling process. The desired results at each time step were transferred to the following calculation module, element by element. The system coupling module managed the data exchange process. I will briefly describe the calculation modules in each analysis type. The electromagnetic problem was solved in the Maxwell 3D module, where a heat loss in the specimen volume produced by eddy current generated by the inductor were determined. The current in the inductor was chosen by the approximation method to obtain a triangular waveform of the temperature cycle in point A, where the pyrometer is aimed. The finite element model was solved in a symmetrical formulation. In the CFD model, fluid heat loss from eddy current obtained from the electromagnetic problem were taken into account to calculate temperature fields. After a heating period of 30 seconds, cooling air was turned on for the next 30 seconds. The impact air jet flowing out of the nozzles fell on the specimen surface. Strain-stress state is calculated in the transient structural module. Temperature non-uniformities in the specimen volume were taken into account. The symmetry and fixing boundary conditions were set for the specimen. The load was applied to the end phase. The properties are set as piecewise linear function of temperature. The figure at the bottom shows the plane of crack growth in the specimen. The calculation results will be shown at three cross-section points P, C and B, and along two cross-section lines, symmetry plane and notch tip. Let us now turn to the calculation results. The slide shows the results of the electromagnetic problem in the form of magnetic fields around the specimen in the upper figure, as well as heat loss are shown in the figure below. It can be noted that the most intense heat loss are realized in the area of the inductor coils, where large values of the magnetic field strength are also observed. Along the thickness of the specimen, heat loss decreases after passing the skin layer from the free surface of the specimen. The calculation results and fluent is shown for the temperature distribution and the most important characteristics of the heat transfer process. The heat transfer coefficient reached values of 20 Watt divided by meter Kelvin during induction heating and 240 during convective cooling. Biot number during cooling reached 0.35, which is served the specimen by a large temperature range in the cross-section. During heating, the temperature range is about from 3 to 5 degrees. During cooling, in the transverse direction, about 15 degrees. On the specimen edge, the heat transfer coefficient reached values of 380. This explains the temperature variation in the specimen. When using specimen with an axisymmetric cross-section shape, for example a circular cross-section, such heat transfer intensification obviously should not be expected. The calculation results were compared with measurements by a thermal camera on the lateral surface of the specimen and shown in the second figure on the left. The aerostream lines and temperature around the specimen at the time of heating and cooling are visualized. One may note that the formation and breakdown of vortex on the specimen edge during air cooling. A comparative calculation shows a more uniform temperature fields in the specimen cross-section when using a rectangular inductor. The structural analysis shows the following interesting features that are not possible to measure during the test. The figure shows the distribution of normal stress and temperatures in the specimen plane. In the most heated areas, thermal linear expansion leads to compression during nominal expansion. At the same time, around overheated areas, less heated and less expanded material takes the full nominal tensile load. At the moment of the highest nominal load and temperature, stress of 490 MPa occur in the notch tip, and after 10 seconds of air cooling, the stress go up 1.5 times. This is explained by an inverse reduction in the thermal expansion of the external surface compared to the area inside the specimen. The configuration of load and temperature leads to R ratio -1 for the out-of-phase type of loading. By comparison, the nominal loading has an R ratio 0.1. The change of stress from time is demonstrated at points C, P and B. To obtain a steady state stress amplitude, it is necessary to perform 3 preliminary heating cooling cycles. It can be noted that there is a mismatch in the phase of the point of maximum and minimum loading with a nominally specified cycle. Under in-phase loading conditions, as a result of the calculation, the R ratio -0.1 is observed at point P. For out-of-phase stress change during 5 cycles, also shown an R ratio -1 at point P. Experimental measured notch opening displacement loops are compared with calculated ones. The nominal normal stress is positioned along the vertical axis at the top picture. In the figures below, the same displacement are located on the horizontal axis, but the calculated stress at point P and C in the specimen cross-section are located on the vertical axis. The figure above confirms the comparability of the calculation results with the data measured in the test. Hence, it follows that the measured data of the notch opening displacement don't describe the strain stress state in the whole specimen cross-section. The loop changed shape under out-of-phase loading, but just as in the in-phase cycle, measured data of the notch opening displacement don't describe the strain stress state in the whole specimen cross-section. We divided the calculated total deformation at point P into mechanical, elastic plus plastic, and thermal expansion. The figure above shows the change in the components of total deformation during 5 loading cycles. Thermal expansion and mechanical deformations are comparable in terms of peak values. However, there is a noticeable phase shift between the peaks of these components. The results for out-of-phase loading are demonstrated in the same format. Under condition of increased load 200 MPa, the mechanical component of the deformation already exceeds the thermal expansion by 3 times. I will list the main conclusions and the recommendations. The main conclusions of the work is: for the correct strain stress state analysis of the specimen under thermomechanical loading conditions, it is necessary to carry out a multiphysical calculations of the heating and cooling process during first 5 cycles. Based on our numerical results, we recommended to use an axisymmetric shape of the working area specimen, or to use a small ratio between width and length of the specimen cross-section. The combination of the period and temperature range in the deformation cycle have to satisfy the tolerance for scatter band of the temperature in the cross-section of specimen in order to exclude the influence of the heat exchange process on the stress-strain state. In order to further apply the results of crack opening displacement measurements using an extensometer, it is necessary to separate the temperature and mechanical components of the total deformation. For the same mechanical loading conditions and temperature range, in-phase and out-of-phase cycling lead to the implementation of deformation cycles characterized by different air ratio values. Thank you for your attention.